All right, so in this video, we're going to solve the following system of differential equations. So, how do you suppose we solve a system like this? Well, one way we can do so is we could use the eigenvalue method. And so to do that, we're going to start by writing this system as a matrix equation. And so this is what we have. This equation is in the form of this, where this matrix is what we call matrix P. So now what we're going to do is we're going to find the eigenvalues of P. So how do we find the eigenvalues of a matrix? Well, to find the eigenvalues of a matrix, to do that, you basically take the determinant of that matrix. Right, but it's slightly modified. Turns out we're going to take these two entries and we are going to subtract lambda, and we're going to set this determinant equal to 0. And so at this point, we are going to solve for lambda. Now, lambda is what we call an eigenvalue of matrix P. And so really solving for lambda, well, the determinant of a 2 by 2 matrix, if you recall, is this times this minus this times this. And so at this point, I'm just going to simplify the left-hand side of this equation as much as possible. And so as you can see, we end up with a quadratic equation. Now, this quadratic equation can't easily be solved by factoring, so I'm going to resort to the quadratic formula. And so this is our result. Lambda equals 5 plus or minus 4i. So we basically have two eigenvalues. So in this particular case, our eigenvalues are complex. And whenever you get the case where your eigenvalues are complex, it turns out you only need to consider one of your eigenvalues. So I'm just going to consider the first one because it doesn't matter which one we consider, we just need to consider one of them. So I'm just going to keep this here for safekeeping. And so what we're going to do is we are going to find an eigenvector corresponding to this eigenvalue. So, how do we find an eigenvector for an eigenvalue? Well, to do that, we could use the following matrix equation. So basically, we're going to use this matrix equation, where lambda 1 is our eigenvalue, and v1 is an eigenvector corresponding to that eigenvalue. So, substituting in the things that we know that matrix P is the same matrix that we've been dealing with. Right, and we're subtracting our eigenvalue, which in this case is 5 plus 4i. Right, and then we're multiplying the identity matrix. In this case, since our matrix here is 2 by 2, we're going to be using the 2 by 2 identity matrix. And so this thing is multiplied by our eigenvector. And since we're dealing with 2 by 2 matrices, our eigenvector is going to have two entries. And I'm just going to call these two entries v1 and v2. And this entire thing is set equal to the 0 vector, right? And since we have two entries here, we're going to have two entries here, where both of the entries are 0. And so at this point, what we need to do is we need to find a non-zero value for v1 and for v2 that satisfies this matrix equation. That's really the whole goal. So to do that, we're first going to start by simplifying all of that stuff. And so if we simplify that into a single matrix, we would get this, right? So we've taken this entire thing, we've been able to condense it into a single matrix. And so really, at this point, we could perform matrix multiplication for these two matrices. So if we multiply these two matrices together, we would get this. And so really, we have two matrices equal to each other. We could set this thing equal to 0 and this thing equal to 0. And so this is what we have now. But remember, when it comes to computing eigenvectors, It turns out once you get to this point that these two equations are actually identical to each other. And because of that, you only have to consider one of them, right? In other words, it turns out that you theoretically have the ability to convert this equation into this equation. And you can actually prove that these two equations are identical, right? But whenever it comes to computing eigenvectors, you only have to consider one of them since they're identical. So I'm just going to consider the first one. And so at this point, what we need to do is we need to figure out a non-zero value for v1 and v2 that satisfies us. And so I like to think of the nicest numbers possible. So it turns out it's going to be nice if I choose v1 to equal 2. If I choose v1 to equal 2, then what should v2 equal? Well, it turns out if you were to substitute v1 for 2, you would have this times 2 plus 4v2 equals 0. If you algebraically solve for v2, you would get 1 plus 2i. So in other words, this number and this number satisfy the above equation. And hence, this would be an eigenvector for this eigenvalue. And so that's what we have now. And so now at this point, we have an eigenvalue and we have an eigenvector. At this point, you're going to need to bear with me because this part's a little bit unclear at first. But we're going to do e to the power of our eigenvalue times t. T is the independent variable that x1 and x2 depend on. And so basically, we're just going to simplify this. If we were to simplify this, we can simplify it by first distributing the t across. And so now at this point, we can use one of our laws for exponents. And at this point, I want you to pay attention to this second factor. Notice that this is actually in the form for using Euler's formula. If you recall, Euler's formula states this. And so in this particular case, theta is equal to 4t. So if we apply Euler's formula to this second factor, we would get this. And so now, again, bear with me. But now we're going to take this thing and multiply it by our eigenvector. And you know what? I'm just going to move my e to the 5t out to the front right here, just so it's out of the way. So basically, we're taking an eigenvector and we're multiplying it by this thing. So really, we're going to basically multiply each of our entries by this thing. We're going to do 2 times this thing and 1 plus 2i times this thing. If you do that, we would get this. And so hopefully you're able to see how we go from here to here. And really, what I'm going to do now is I'm actually going to simplify what we have in this bottom entry, because as you can see, it still needs to be FOILed out, right? Because we have to FOIL this and this. In other words, we're going to do this times this, plus this times this, plus this times this, plus this times this, right? And so if you were to do that, here's what you would get. At this point, I'm going to group together my real terms and my imaginary terms. And so this is what we have now. What that means is we can replace this thing with this. Right, so basically we replaced this with this, right? And that's what we have here now. And so now at this point, I'm going to move back up to the top. And I'm going to show you how we can get our final answer from this. And so there's really 2 parts you need to be able to take away from this. We have a real part and an imaginary part. The real part consists of these 2 entries, and the imaginary part consists of these 2 entries. I'm going to call this the real part of our solution, and I'm going to call this the imaginary part of our solution. Now, by the way, the imaginary part of our solution is not going to contain the i's, right? And the real part and the imaginary part contain the e to the 5t, right? I just decided not to distribute it across because otherwise it'd be a lot more work for me to write, right? And so it turns out that our general solution can be represented as, and so now I'm going to perform the substitutions. So for the real part of x, it's going to be a matrix consisting of these two entries, and technically it would consist of the e to the 5t as well, but I'm just going to move that e to the 5t to the outside like that. Right, and then we have plus c2 times the imaginary part of the solution, which, again, is not going to contain the I, but it's going to contain the e to the 5t. But just like for the real part, I'm going to move the e to the 5t, or I'm going to keep it on the outside like that. So basically, we're going to write these two entries without the I. And so this would be our final answer, right? This would be the general solution to this system. And so it's pretty cool, right? When you have complex eigenvalues, you end up with sine and cosine, which is pretty cool in my opinion. So this is basically it for this video.